Today, I want to talk to you about the biggest remaining mystery of our universe. So let me start with a sort of unconventional introduction by a set of cartoons. So now we have a star. Suppose we know how large the star is and how massive the star is. However, astronomers found out something extremely weird. There is a moon orbiting around this star. But the speed of the orbiting speed is much faster than it is allowed. This is troubling because the physics here is extremely clear. If we know how massive the star is, and if we know the distance from the moon to the star, then we can calculate the exact speed of the moon. The fact that it's traveling faster means something that is fundamentally wrong. Could it be there is some invisible dark matter actually surrounding the star that not only to our eye, but also to modern telescope? So far, nobody has found out this dark matter yet. However, it is extremely important not only to physicists, but also to everybody else. To illustrate that idea, let me give you a concrete example. Suppose a family trying to visit a distant planet for a vacation, for example. And in order to go there, they have to go through a star. So they can calculate, based on how massive the star is, they can calculate the safe distance. As long as they are away from the safe distance, they won't be worried about getting gravitationally pulled to the star. However, because they don't know the existence of dark matter, there could be a dark matter cloud surrounding the star that's giving way stronger gravitational pull than anticipated. So instead of going to a distant planet, they're actually gonna, unfortunately, pulled to the star, and it's gonna end up in a tragedy. To avoid tragedy in the future, we have to study dark matter now. Also, by the way, the artist responsible hand drawing all these pictures are actually sitting in the audience today with us. Okay, so how do we find dark matter? So I have two pictures above. The picture on the left is our underground lab in Canada, which is 7,000 feet deep underground. The reason we put deep underground is we absolutely do not want any background noises. And the picture on the right is my colleague Dan is trying to assembling the actual detector inside that lab. So I've told you that nobody has found dark matter yet, but that does not mean we make no progress at all. In fact, after each run, we can draw an exclusion plot, as shown here as an example. So basically what it means is, even though we do not know how massive dark matter particle is, we can suppose it has a certain mass. And if it has a certain mass, we can know the chance of collision between dark matter and ordinary matter has to be lower than the curve as shown. So let's divide the curve to be region A and region B. The region A means if dark matter exists, it cannot in those regions because the chance of collision has to be lower. Otherwise, we've already found it. So the dark matter has to live in region B. Now, the research becomes, we are trying to push this curve to be as low as possible. So if you find the lowest point, the x-axis, it depends on the type of detector you're running. So we have certain type of detector. We also have some competitors running different type of detectors. So for us, we are like complementary to each other because we have different x-axis. But also more importantly, the y-axis depends on how low you can go, depends on the detector sensitivity. Now, how do we improve our sensitivity? The most straightforward way is just to build a bigger detector. However, the only issue is that it costs a lot of money. And you can see in the picture above, it's already pretty big. Remember, we have to put our detector inside deep underground. There's a lot of logistic issues, among other things. So the detector already costing hundreds of millions of dollars. Is there any cheaper way to do things? Yes, there actually is. We just need a better calibration. And to that end, we just need to get a PhD to do all the work, like me. So now I'm going to shift in gear, talk about my actual research for the last four years. OK, To understand the sensitivity, we need to understand when the dark matter hits our detector, we have a chance to see a signal. The chance is highlighted because no detector can claim 100% efficiency. So if we understand our efficiency better, we can naturally claim better sensitivity. So this is the sort of plot we use to study efficiency. The x-axis is the potential collision damage, collision energy between dark matter and our detector. The y-axis is the chance we see an actual signal. The dashed line here is only the minimum energy required for our detector to function. So for years, we don't really know what this response looks like. So scientists have proposed different models. For example, this linear model, a step model, or exponential model, or some fancier sigmoid model. The point is, we don't know how it will look like. Eventually, it will become 100%, but when? Nobody knows. So we have different models and trying to fit the data. However, there is a problem. The problem is none of these models are particularly well physics motivated, and each model has the intrinsic uncertainties related with it. And then unlike many other fields, in the precision measurement science, only the worst case scenario count. So we have to consider the really worst result. That makes us really bad. And how to solve it? My proposed way to solve it is without any pre-imposed model, let the data speak for itself. So this is my proposed generalized model. Instead of predefined functional forms, I only have 5 tunable knobs that can float from left or right. That is supposed to mimic all previous models and even more. For example, if the real efficiency curve looks like a linear function, it can do it, or step function, exponential function, or sigmoid function. It can do all of that. Then, I suppose, I can let all these knobs do random walks with the only condition that after a certain walk, it calculates the best fit before and after the walk. If after a certain walk, the efficiency it becomes better, it will more likely to stay in the new position. If it's worse, it's more likely to revert back to the original position. So in statistics, this sort of process is called Markov chain. While it's already well studied 100 years ago, the only limiting factor is it requires a huge amount of computing resources, which is not possible until very recently. So I have set up this problem and select to run for random walks for millions of steps. Now let's see what happens. So this, I'm showing 200 steps. So it's sort of trying to figure out where it is. 1,000 steps, 5,000 steps. Actually, I've run it for millions of steps. I'm not showing all of it, but you already see the data actually figure out where the best fit region is and the related uncertainty with it. Then we use this sort of information and to put that information into our exclusion plot. Just a gentle reminder, before we can make the discovery, the exclusion plot is the most important criterion for dark matter scientists. So this is before my work. My collaboration is called PICO in the blue lines. Right now, this looks really bad for us because there is a black line called L, which completely covered our region. Means everything we excluded is actually already excluded by L. However, after my calibration, this is the impact. Our curve become pink and become significantly lower. In some cases, it's a factor of 10 lower, and we surpassed L, a certain region in the plot. So now we can claim, with my calibration, we can claim we have the world's best dark matter detection limit. That concludes my talk. Thank you.